Okay, so we defined index of differential forms. Now here comes the theorem. Theorem. The Poincaré-Hopf Index formula for real differentiable forms. Okay, here is the statement. Let C be a smooth, compact surface which is orientable and having no boundary. Let lambda be a differentiable one form. Which is smooth except if at a finite number of isolated singularities then the conclusion is that the sum of the noktaları da isolated singularities, bu noktalara isimler vereyim. P1, Pm, then the sum of this indices is chi of C, where so it is not zero this time. Okay, this gadget is 2 minus 2g. G is just genus of the surface. C is the Euler karakteristik. So, for example, so if your surface is a two-sphere, I don't consider a Riemann surface, just a two-dimensional surface, the ones you have seen in advanced calculus. Okay, smooth surface. For example, for the sphere, if you choose a form like this, and suppose it has, you know, some singularities. Singularity means what? Around this point, the form can be something like this. For example, suppose this corresponds to 0, or maybe, you know, under some coordinate. So it is like this: x minus 1 dx plus dy y squared plus 1. You see, when x is 0, you know, suppose I have a coordinate system here, and when x is 0, gerçi bu iyi olmadı çünkü isolated değil bu. Şöyle diyeyim: x minus 1 squared plus y minus 2 squared. So suppose this point corresponds to the point xy, and coordinates are 1 and 2. So this differential form, you know, blows up at this point. So it's not well defined at that point. It has a singularity. And this theorem tells us that, you know, suppose I have, you know, several singularities like this. If you just add them up at the indices, you just get Euler characteristic of the two sphere, and Euler characteristic of two sphere is just 2. 2 minus 2g. G here is 0. Genus is 0. If it was, you know, the nice thing about this theorem is that, you know, this is an analytic object, right? Index of differential form is an analytic object, but their sum is not analytic. Their sum is, well, of course it is analytic, but it's a geometric or topological invariant. If your surface is like this, efendim, P1, P2, Pm. So this is a torus. It has genus 1, and the sum of the indices this time is just Euler characteristic of 2 torus. So our surface is just 2 torus. So this is 2 times 2g. Well, g is just 1, so 2 minus 2, this is 0. And for the other surfaces, if genus is larger than 1, then index will be negative, right? So let me, another example. Suppose your surface is sigma g, and g is at least 2. So I have this 1, 2g. Then the sum of the indices it is just the Euler characteristic. Bu arada teoremi yanlış yazmışım. I am sorry. This is negative Euler characteristic. I'm sorry. So this will be negative. Well, this is still 0. And this one will be what? Minus 2 minus 2g. 2 minus 2g is negative because 2 is larger than, sorry, g is larger than 2. But I have another negative sign, so this is a positive number. So for the sphere it is -2, for the torus it is 0, for all other surfaces it's a positive number. Okay. We will not prove this theorem. It's a theorem about, smooth manifolds, but I can give you some idea why this is true. When you have a differential form, let's say, axy dx plus bxy dy, basically taking its dual, you get a vector field. So you get some a prime xy del del x plus b prime xy del del y. Bunlar tabii türev değil. İsterseniz şöyle tilde diyeyim. Tamam mı? Türev değil. So it's like dual, right? So any differential form actually can be regarded under a suitable isomorphism as a vector field. And then zeros or poles of this becomes zeros or poles of the vector field. And for vector fields, the formula for this, for the indices for vector fields, the index sum of the indices, the sum of the indices is not minus a Euler characteristic, but Euler characteristic of C. So when you take the dual, you pick up a minus sign. I will not explain that, but let me explain this, okay? So for a vector field, this number is the Euler characteristic. You basically do this, yani bir şey yapayım. Şeyi üçgenleyebilirsiniz surface'ınızı. You can triangulate your surface. Okay. And when you triangulate your surface, you have vertices, edges, and faces. Euler characteristic is just the sum of vertices minus sum of edges plus sum of faces. So how many faces you have, how many vertices, how many edges, you just count them and then form this alternating sum. Okay? Euler. And on a triangulated surface like this, you can form a vector field. How? Well, just choose the midpoints of these edges. Okay. Ondan sonra da şöyle bir vektör alanı kuruyorsunuz. Bir de şunların da böyle merkezlerini alın. Üçgenlerin. You form the following vector field. From this midpoint of the edges, you go towards the vertex. Therefore, for each vertex, all the vectors are just coming towards the vertex. Here, we here we have a source, so it goes like this. So at this point, at the vertices, all the arrows are going like this. So this is a vertex. At a face, it has a 0 here, it has a 0 here, and it has a 0 here. At these vertices, at the faces, center of the faces, all the arrows are going like this. And at the other points, edges, you have such kind of vectors. So one direction is going away from the origin, and the other directions are coming towards the origin. So it is like this. So vector field is like this. Okay. So this is the vector field stuff you have seen in 254, basically. What is the indices of this? Index of this. So this is just, you see, this function is just xy goes to, minus x minus y. It will have index 1 if you compute it. Yani bunu yaptık, bu hesapları. Yani çemberin etrafında bir tur dönerken bu ne yapar? This is just, you see, xy here, minus xy is here. So this gadget is just rotating this circle pi radians. Therefore, as you move around the circle, you just move around the circle counterclockwise. So index is 1. Here, what is this? This is the identity map. So index is 1. What about this one? So in one direction it goes like this, and in the other one it's the other way. So this is just minus x y. Değil mi? X yönünde giderken tersine gidiyorsunuz ama y'de aynı yönde gidiyorsunuz. Yani kabaca. Bunun indeksini hesaplarsanız index we computed this, right? It is minus 1. So every vertex counts as 1. Every face counts as 1. Every edge counts as minus 1. So the sum of the indices my PJs are, these points, the midpoints of faces and edges, and the vertices. So this means what? For a point which is a vertex, it is 1. Therefore, here this is just the sum of the vertices. And then for points like here, I mean on the edges, so if pi is this point, it will be minus. Therefore, this is sum of edges plus sum of faces. But this is just the Euler characteristic. This is not a proof, but an explanation for one vector field. You may ask, of course, what about other vector fields, right? Herhalde homotopi şeyi yarar mı ki orada işe? Ya tabii. Yani tek üçgenlemesi bu değil tabii. Şey. Okey. Evet. Okey. What about for meromorphic differentials? So our aim was to prove this theorem. The Poincaré-Hopf Index formula for meromorphic differentials. Suppose C is a compact Riemann surface. In particular, it's a smooth-oriented manifold, two-dimensional, surface without boundary. It has no boundary, compact Riemann surface. And omega, a meromorphic differential form. Well, meromorphic differential form is, of course, it's a smooth differential one form. No, for vector fields, it is plus. So the minus sign changes here. If you add zeros or indices for the differential form, it is minus Euler characteristic. When you pass to the vector fields, it becomes plus. So there is, I don't want to, talk about that. So when you take dual, usually you pick up a minus sign. Daha sonra açıkladı. Later we will see why this is the case, okay? So, and then what is the result? Toplam. İntegral yazmışım da. Minus the Euler characteristic. So this is just the application of the theorem, which I have described it a little bit. It's an application of that theorem. Let's see why this is true. Assuming the Poincaré-Hopf theorem for smooth surfaces. Okay, now, so all right, so let's say our differential form at some point it is okay, şöyle yazayım. Assume that near a singular point şeye de dikkat edin. For differential forms here we talked about singularities, but here I counted zeros. So singularities of the differential forms are translated to the zeros of the vector field. Okay? O da şundan, the reason is this, when you feed your differential vector field to your differential form, let's say these are dual elements in some basis. This is one. If this has a 0 at some point, so this becomes 0. Therefore, it should be infinite at that point so that the product, right, is 1. Yani sıfırı neyle çarparsanız 1 olur. Sonsuzla çarpmanız lazım. Okay. Yani şöyle, sıfırı neyle çarparınız? Bunu 1 yapmak istiyorsanız 1 bölü z ile çarparsınız. Bunun 0 var, bunun polu var. Tamam mı? Yaptığımız şey o. Okay, singular point. P of W. We have since any meromorphic function is just a meromorphic function times dz, and that meromorphic function, indeed this is something like this, and this function has a pole. Pole means what? This thing is written like zw and then some a0 plus, something like this, and this is analytic function, analytic, and it is not 0. Since it is analytic and is not 0, I can write this as e to the power f. So this is just z to the power like this, e to the power f of z, and this can be written like just d times e to the power f of z divided by nu to the power nu. And then I just call this gadget z, okay, basically. So I can write any meromorphic differential form in a suitable coordinate like this. I can just absorb this expression inside the variable. Okay. Şimdi bunu sileyim. Bunları daha önce zaten defalarca konuşmuştuk. Şimdi ondan sonra şunu yapacağız. Let lambda to be real part of omega. Well, z'i r times cos theta plus I sin theta diye yazarsak z to the power nu is just r to the power nu, and then nu to the power of this is just cosine nu theta plus I sin nu theta. Therefore, this is the real part, and this is the imaginary part. So the real part is r to the power nu times cosine this. Okay. Yok, bu şey değil. Tabii dz'i de var bunun. Şöyle yazmam lazım. I'm sorry. Well, okay. This is z, but what is dz? Dz is just okay, dz'i şöyle yazayım. Dx plus I dy. So okay. W'yu şöyle bir daha yazalım. Okay, this is r to the power nu cosine nu theta plus I sine nu theta, and then dx plus I dy. What is the real part of this? Real part is this times this minus, because I will have I, this times this. So the real part, so the real part is just lambda, which is just the real part, is r nu cosine nu theta dx minus sine nu theta dy. Right? Yani işte real part'ı dx ile bunu çarpıyorum. Dy ile bunu çarpıyorum. Sorry. Oh, yes. You're right. So let me correct it. Here, this r to the power nu is outside the parentheses. So the real part, dx times this minus dy times sine times r to the power nu. So it is just this gadget. Now, okay, this thing can be written cosine nu theta dx, sorry, minus dx plus sine minus the dy. So to get rid of this minus sign, I just put it inside. Here, this is cosine, therefore it doesn't matter whether you have minus or plus. The important thing is that, you know, here instead of theta, we have minus theta. So as theta increases, minus theta decreases. So there will be a minus sign, and by direct computation, index of lambda is just minus so this number. Neden o da? You see, I mean, as theta, so suppose nu is 3, okay? As theta goes from 0 to 2 pi, what about 3 theta? So if theta goes from 0 to 2 pi, 3 theta goes from 0 to 6 pi. So it just goes around it, around the origin, 3 times. And you have minus sign because here, this is your positive direction, theta, but you have minus theta, so it goes the other way around. That's why you have this gadget. Hence, thus, well, instead of this gadget, I can just write minus the indices. But I know that for any differential form, this sum is just minus the Euler characteristic. Minus the Euler characteristic of your surface. So this is just x. Bir dakika. Yok, burada hata yaptık. Nerede hata yaptık? Ee, pardon. Orada ben yanlış yazmışım. Özür dilerim. Şurada söylediğim şey yanlış. Sorry. Okay. So this is positive. Therefore, this is negative. So let me write here as a correction. Yani o hesabı yapmamıştım. Orada yanılmışım. I just copied wrong from my notes. Correction is that for a differential form, it's like zeros. This is not minus Euler characteristic, but it's Euler characteristic. So this is plus, okay? So please correct in your notes. Therefore, this is like this. And ilginç. Neyse. Yani oradaki şey lafı çok doğru değil. Onu söyledim. Hani o hesabı yaparken when we are trying to prove this, we pass from differential form to vector fields. I said the sign should change. But I guess for real ones, it doesn't change. For complex ones, it does, but yeah. Okay. So this should be positive. Okay. Şimdi bir sonraki şey kompleks manifoldlar. Biz ama bunu zaten neredeyse yaptık gibi. Neyse. Bugünlük bu kadar olsun. Ya yeni şeye başlamayayım.